Big Imaging, Lecture 10. This is a pre-recorded lecture to replace the lecture that was intended to be on May 8th, 2025. Today's lecture will be about bimodal experiments and some software engineering that can be quite useful when you start doing your projects. As usual, we have some literature you can take a look at. The typical one is always John Ross, which has a lot of ideas. But now we can also add a couple of books on the topic of image fusion and image registration, and they can be quite useful in this topic. Finally, we also have a couple of references on software engineering, and mainly one is about testing in Python, and the other one is a way how you describing some guidelines how to work in software development collaborations. So until now we have done quite a lot. We have already gone through, in principle, all image processing that is going to be taught in this class. And we started out with looking at images, image enhancement, how to highlight contrasts of interest in images. Also segmentation, and from the segmented images we went on working on component labeling, which gave us items that we can analyze for shape and different things, and also looking into more complicated shapes using skeletons and watershed segmentation. An application is actually going towards dynamic experiments, and there we look into time series of images and what they can produce, and also which problems they can introduce. Important for the dynamic experiments, and actually also for today's lecture, is image registration. And finally, a topic which is about wrapping up what you have learned from the images is statistics. You never get around doing a statistical analysis in order to tell if your hypothesis is correct or not. So today's outline is first a bit motivation, why working with different modalities. Then we have some scientific goals, looking into some image fusion, how you can fuse images, and also looking into bivariate segmentation, where you have images from two different modalities and want to use this information in your segmentation. Finally, I'm going to go into some software engineering that supports your repeatability, and that is the second topic of today's lecture. So, usually we are working with a single modality, and some modalities are more suited for specific topics. And here I have actually mainly applications of neutron imaging, but you can find similar separation in other modalities. So in this case, I'm looking into hydrology and in soil and geology. And here we want to segment with some accuracy and also estimate water content. Cultural heritage is a wide field that is used in imaging, where imaging is used. And again, we're looking into segmentation accuracy, but also material classification, and all these this can also introduce a lot of troubles when you work with these images. Building materials is quite similar to the soil and geology. Again, we look into water estimate and dimensional changes. So there can be some swelling in the material, which introduces some problems, in particular when you're looking in the time series and things are moving around when they shouldn't, or at least not from the analysis point of view. In material science, we have the problem of penetration power. So is our chosen image modality, can it actually go through the material? And sometimes we don't really know exactly what we see. So we can get some ambiguous readings. Same gray level may actually have different meanings depending on where in the sample you look. So, reasons to select a specific imaging modality are different, but you can, in principle, split them up into the positive side, reasons to select it, where you look for good transmission, good contrast, also that all relevant features are visible, so that is actually also related to the good contrast, but also to the resolution. And in some cases also that you can identify different materials. Reasons not to choose a modality are, of course, low transmission. You cannot look through the sample as you would like through. Then the contrast between relevant information is too low, and you can't really resolve it in any gray levels. And if not all features are visible, well, then it's quite useless modality. And you can maybe also get some ambiguous response that the same two different materials give the same gray levels. So until now we only worked with single modality, so now let's take a look at what is it actually we have in our imaging experiment. So usually from the experimentalist point of view, you have your application and you want to have your answers. And the application then has its own physics, but it also has, the sample also has some interaction with the material. And then we look into the physics of the interactions. Then at some point you need to acquire information. So then you need also to have an imaging system that actually can resolve both in space, time, and actually also in contrast the relevant features. Finally, you need to have some processing workflow, which is actually what we have been working on in this class. And here you also need a strategy which in some way also relates back to what all the other three can do or require. So let's introduce multimodal imaging. So what we want is, in one way, is extending range of operation. Maybe you can penetrate with one modality. You can penetrate the material better, but you may possibly have lower resolution. Then extend the spatial and temporal coverage means that you on one side can have larger field of view with one modality than you can with another one. And the temporal coverage is also that there are some timing limitations when you acquire images. So one modality, it may be better to do fast sequences, but then at lower resolution than another modality. Then of course we want to reduce the uncertainty. So usually one way to reduce uncertainty is to add more information. And this information could come from a different modality. And with that also, we also would increase our reliability in our statements. So let's look at some modalities. Here I'm showing neutrons and X-rays for material science, and you can see this camera on the picture. You have one image here with the neutrons and one with the X-rays. You can already see by your eye that they actually respond very differently. So for example, looking here, you should see the film roll, but the X-rays don't see it because it's too low density. Neutrons, however, that are sensitive to hydrogen, sees the plastic very well. And also, if you look in this area, there is a lot of metal, and the penetration power of that for neutrons is much better than with the X-rays. So if we combine these, we can actually maybe see some details in a better way. And below you can see also how the attenuation coefficients look like for the neutrons and for the X-rays. And here it's about finding relevant combinations, which elements are actually suited for doing a bimodal investigation. Another one is to look into grating interferometry, where you can get not only the transmission from the experiment, but you can also get a differential phase or dark field contrast. And these are related, but still the contrast mechanisms are very different. And that can also give you a possibility to see different things. This is generally also in radiation transmission type of experiments. So X-rays, neutrons are using this technique for acquisition. Another way to look at a sample is through spectroscopic imaging. It's not really multimodal, but you get much more information about your sample, and that can actually be used in the analysis of the samples. And if you look into medical imaging, the typical modalities we are talking about are MRI, X-ray computed tomography, PET and SPECT. And they provide different informations, and by fusing these informations, you can learn more about the patient's condition. And in some cases, as you can see here, the comparison between MRI and PET is that the PET is very fuzzy, low resolution compared to the MRI. But if we overlay the PET on the MRI, then you can see also the anatomical structures that are related to the response in the PET. And the same goes also for combining MRI and SPECT, and then you can also get the same kind of anatomical background information combined with the functional information from the SPECT. In biology and microscopy, we also have different modalities to work with. So in this example, we see a combination of the same specimen with fluorescence microscopy, electron microscopy, and also nanosims, so that is nanoscale secondary ion mass spectroscopy. So you get, in principle, you get here isotope information in the sample. So these are still now, the example I gave, they are on the same dimension, but you could also consider mixing information that you have scalar information, and you can also have surface information combined with the acquisition, and finally you could also combine single radiographs with computed tomography data. And that would make it possible to measure temperature, flow rates, pressure, etc. in your data. And fusing those will give you more information about the sample. So I have already mentioned fusion, and that is in principle a way how you can combine information from different sources, and finally with the aim to obtain more information about the sample. And that is the aim of the whole fusion, and you can read more about it in this book by Mitchell. Actually, he wrote a couple of books on the topic of fusion. And when you go into fusion, there are no golden recipe. One way does everything, as you have also probably already noticed in image processing in general. And here we can look into different strategies. So for example, multivariate fusion, where you actually take it pixel-wise or at least spatially compare the data using the same kind of concept. It can be segmentation methods or estimation. Another way would be to use augmented fusion, where the modalities have different functions. So one modality can be used to guide the other one in order to get more information. Could be that you have very fuzzy edges, like in the case of MRI and SPECT, where you saw that it was very low resolution. So here you can identify which regions are relevant in the anatomy, and then plug in the information of the second modality. You can also use Fusion to reduce artifacts, so can use it, for example, to fill in the blanks or also to identify artifacts in the image. And that can also be a useful method. And of course, as always, you can always combine all together and get the final result, which is often actually happening. And which strategy you select is determined by, naturally, experiment objectives. Why do you want to do your images? And also how you want to look at, so what hypothesis you want to answer. Then another thing is what is a sample composition, what materials do you have, and how can they actually interact with each other. Finally, the condition of the data, which also comes into the artifact reduction or maybe denoising. Then you may need the support from a high SNR technique to get the answers from a low SNR technique. And if you go into more abstract categorization, you can look at different levels of fusion. So the first level is the one that comes most natural, is the data to data, is when you have two images, fuse them, and you get an image out. The next level is of abstraction is that the data results in some kind of features, and that could be that you work with some multivariate segmentation and result in items in the image, and these are the features that you want to analyze further. Then you can also go one level higher, so you have features extracted maybe on level 2 or even separate, and then you combine those in order to get more fused information. The higher levels are about decisions, so then you are on the level that you do hypothesis testing based on features, or even make a cluster of decisions from different modalities and merge them together in one framework. So for example, one example would be to work with a random forest where you have different segmentation trees, and then you merge the data from these trees. The image fusion workflow is quite similar to, at least in the beginning, to the dynamic experiment. So you start with your image acquisition, and the images can be of different shapes, different gray level, depths, etc. So what the first step you need to do is to register the images, and as you know from the last lecture, registration means that you do a lot of transformations, rotation, translation, scaling, and so on, until you have the two images on the same orientation. Then you go into the pixel fusion and work on first aligning the images, and then you may need to do some radiometric calibration, which means you have to adjust the gray levels. Maybe a plane normalization would be helpful here. And then you compare pixel by pixel. The next level, you have extracted some features, and you may need to do a radiometric calibration again. And in this case, you look at different objects and compare them between the two modalities. And finally, we have the decision fusion, where you have decisions and labeling. So all these fusion techniques can be worked with individually or in a combination, and the aim in the end is to get a result where you can have your statistics or do some modeling based on the fused data, or else you can also go towards presentation and display of the data for a more qualitative view. Usually you have a good plan, but it could even happen that if you mix in too many modalities or mix them in the wrong way, you can actually end up in something that is labeled as catastrophic fusion. And maybe if you do it wrong, the combination of the different modalities end up in worse performance than if you have them on their own. So don't fuse just because you can, may not be needed. And that can be caused, the catastrophic fusion can be caused by either selecting the wrong variables, or maybe combining them too complex, or that in some sense the sensor information is cancelling. Could also be, for example, that when you do registration and have cost functions that are counteracting each other, and nothing can really happen. So watch out for these faults when you are trying to fuse data. So this is a bit a recap from the last lecture. We also in image multimodality imaging, you need to register the images, otherwise you can't compare them. And the process is, just as a reminder, we have a fixed image and then you have a moving image. In this case, we have a neutron slice and an X-ray slice of the same sample. And here I choose the X-ray to be moving. So first step is to rotate it so it's aligned more or less in the same way as the neutron image. And finally, we also do some rescaling and cropping, so we have it actually on the same scale. And the problem when you do this is you can see that some features, like the container, is not very well visible in the neutron image, whereas it's very visible in the X-ray image. And this gives you trouble when you try to do the registration. So there are different ways how you can do it. We learned already that registration is an optimization problem, and thanks to the nature of images, it's very easy to have many local minima in this optimization process. And in some cases, a good starting point may even be a manual or guided registration, so you're closer to the true minimum. And then afterwards, you can get the automatic part running. And the first part is, well, of course, you can do it fully manually. There you will probably lose some precision, but what you also can do is you can guide and identify landmarks, points, lines, planes, etc. And in that way provide a course pre-registration. Then afterwards you go into the automatic registration, which includes the iterative process of moving the images towards each other. And here we again need really to look into the metrics that we use, and also think about that in the multimodality framework we may lose some of these landmarks that you could identify in one modality. So you have to watch out that you really have landmarks that are matching between the two modalities. And here, of course, the cost function is of high relevance. And in the last lecture, we started out with a mean squared error. And if you work with images with different modalities, this can be quite misleading. We saw already on the container of the sample that in one modality it was almost not visible at all, and the other one it was shining. And this gives you, by nature, a very large MSE, and that can be misleading for the segmentation and for the registration. So typically we need to have contrast insensitive metrics, and some mentioned in the literature are mutual information, cross correlation of gradients, which is actually an interesting thing, because if you look at the gradients, then you are looking more on the structures than on the bulk of the material, which has maybe more fluctuating contrast. And one that could be interesting is, for example, that you work on these key points identification and try to identify those. But in the beginning, you should try working with something that is looking for mutual information, or also the modality independent neighborhood descriptors. So these are the methods that you could think of. And as an example, this is actually a semi-manual registration, but looking into the fusion of data, we had this dagger, which was found in the Lake Zug. You can read more about it in this paper. There is even, I think, on YouTube, a nice rendering movie that demonstrates this sword. And the workflow was first to register the datasets using in the interactive analysis tool VG Studio. There are many tools. VG Studio happens to be the one that we use in our group. There are also open source tools like a 3D Slicer, which can do the similar task. So what we did some also interactive guided segmentation. So it's an region growing approach where you work your way through the sample. Can be useful if you have low contrast and need a lot of domain knowledge to segment the object. And going on, looking at the visual and qualitative approaches, let's look at this snail shell, which again I have the neutron and X-ray data from. And the X-ray data is actually a bit blurred. I think it's actually because of a not perfect calibration of the X-ray system. But for this purpose, it's okay to work with, because I just want to show the principle of a couple of methods. So the first one is to visualize with the help of a checkerboard. And here is some code that you can use. And in principle, the principle of this is that you alternating the two modalities in this checkerboard and visualizing them together in that way. And looking at the result, when we combine them, we have the neutrons on one side, X-rays on the other side, and here's the checkerboard visualization. And here you can see how well aligned the object is, and also how the contrast differences are within the object. This is very useful as a visual quality check for your registration, but in some cases can also be useful in presentations to give an overview of how the two modalities appear within the sample. Another way, which is also a visualization method, is to combine the color channels of color images. Typically, when you store a color image or a picture, they are stored in the RGB model, which means red, green, and blue color channels. But if we kind of take over these color channels and use them for our modalities instead, we can put, for example, the red for modality A, the green for the modality B, and blue is the average intensity of the two of them. And of course, to combine these, you may have to do some calibration or normalization, because otherwise one may be too dominant and it's, for example, only red because modality A is so much stronger in the intensity, or scaled in that way that you don't see any green. And combining these with the help of channel mixer, this is the code I wrote as an example. Here you can see I do a min-max normalization, and then we combine. Image A goes to red and B goes to green. Here we have A to blue, and B goes to green, and finally we have also A goes to red and B goes to blue. This is a nice way of showing if you, for example, have water in some porous medium. So the porous medium turns out to be brownish and the water turns blue. And that's a quite nice color coding, actually. So now we have shown a little bit how you can visualize it, but still we haven't done any analysis. And the first thing that comes to mind is the segmentation, where you can use the two modalities together. And typically when you're working with an imaging modality, you have seen the histogram, you have two classes, the blue and the red here, and they are overlapping, so the summed histogram of the contributions is just a single mode, which makes it very hard to make a threshold. You have a lot of misclassifications, as you can see here in this blue area, and all that we want to avoid. So now let's add a second modality, or at least look at a second modality. We still have modality A here as before, and modality B has, in this example, flipped the contrast. So now the blue contrast has the higher intensities and the red contrast has the lower intensities. But still we have the same overlap and also a single mode of the histogram, which is still quite useless. So we can't use them segment with each one individually because it will not give a good result. So instead, we can look at the bivariate histogram, and now you can see that even though the single modalities only give a single mode in the histogram, you can see that they are very well separated if you look at the bivariate histogram, which is actually co-counting every pixel and producing a histogram that is two-dimensional. And now we can, with quite good confidence, say that the threshold is at this place here, and we can do a nice segmentation with much less misclassifications. So let's look at an example. We have here roots in soil with I have a neutron image and I have an X-ray image. And you can see that it's very complementary. On one side you have something that looks like a hole here and something that is brighter. In this case it's actually a root. If you look at the X-ray, you can see that what we saw as a hole before is or must be something denser because it's coming out bright, so it's probably a stone of some kind. But the root turns just dark because it's a void, or for X-rays it appears to be a void. So we want to look at what is the combination of these two. And the bivariate histogram here is also much better separated. You can see in the single modalities there is a lot of overlap. You cannot identify the three classes very well. And looking at this bivariate histogram, we have one peak here, which corresponds to the background. Then we have a very wide part here that is a soil, and then this one is corresponding to the container. And finally, the roots are very underrepresented, so it's a very unbalanced data. Roots or blood vessels in a bulk material is usually the least represented kind of pixels in the image. So what we can do is looking into different segmentation methods. We can set up some hypothesis testing based on all these classes. You can do multivariate hypothesis testing for the different classes. And if you want to read about that, there is a good reference by Duda-Hart and Stork. And here you can set up likelihood ratios, for example. That would be one way. But what we also can look at are segmentation methods that we have looked into before. So we have the k-means, we have k-nearest neighbors, regression, and also neural networks and deep learning can be very helpful in this task. So let's look at an example, and here I introduce a new method, which we haven't looked at before. It's also a kind of a clustering type. And here it's about finding or fitting the distribution of a set of Gaussian functions or distribution functions where we have different averages and covariance matrices, and they will together describe the shape of different materials. So here is an example where I have one Gaussian blob here, a bivariate Gaussian, and I have another bivariate Gaussian down here. And if we try to run these Gaussian mixture model functions or fitting, then with two classes, it clearly identifies these two classes. And if we add more classes, as you know, the segmentation becomes more and more fragmented. And the same happens also with the multi or overfitting of Gaussians. So here we have the mixture of three. First step, it tries to split the more elongated class and maintain the more compact. If we add yet another class, then it starts splitting also the compact one into two classes and still keep the other two. Finally, with 5, you get tinier and tinier groups, and it makes less sense actually in the practice. So how can we use this now? We have now got from the Gaussian mixture model, we got a set of Gaussians with their parameters, and now we want to see, we have a point in this training data. We have a point in our image which we want to relate to the training data. And the easiest one is just to take our data point, which has some intensities. In this case, it looks like -2 and 1 or something like that. And now we compute the Euclidean distance from this point to the average position or the centroid of these Gaussians. And that can be repeated for every pixel in the image. And then we have our segmented image. But as you can see, it can come to some ambiguous classifications and of course misclassifications. So stepping up, we know actually more than the centroids. We know that we have a Gaussian shape and that it's oriented. So the next step would be to use the Mahalanobis distance, where you not only look at the average, but also the covariance matrix. And then you can more easily see that the distance is more, or the dot is more overlapping with one class than the other. It's more likely to be in that class, and that gives us then the class assignment. Can be made even more complicated, but it also requires more data from the image, is the Bhattacharya distance. And here we have again with the shape of the two distributions, but also the measured point. We provide information about shape. So for that you need to compute also the local statistics, not only the point itself, but you also need to actually extract the local covariance matrix, and that needs some data. So your resolution in the image is suffering if you would do it like this. So I would tend to say that the Mahalanobis distance makes sense. This one, if you want high resolution segmentations, makes less sense. So, but it comes from use case to use case, so you have to select what is actually fitting your task better. So here we see them together, all the way you have the Euclidean distance, which is just a single point versus points. Here in the Mahalanobis distance, you have a point versus two distributions. And finally, you compare two distributions, the likelihood of the overlapping. So going back to the root data, here I applied segmentation with Euclidean distance, and we have our different classes which we have assigned, and you can see that they are a bit tilted or slightly slanted around here, and that gives us the decision space which is separated linearly between these different classes. And if we look at the segmented result, you can see that the bulk is nicely turned into brown, which is expected. The roots in the sample, they look pretty okay. There is some misclassification towards the gray, but that is also to be expected because they are neighbors and they are quite close to each other. What is curious, however, is that you get this soil on the outside, so it looks like you have a dirty container. But that is due to the low resolution and multi-class segmentation, as you may remember back to one of our previous lectures, where I showed that we can get this skin effect. Another thing is that roots close to the container also turned into the container class. And the reason for that is actually that we have some beam hardening in the images, so it's actually an imaging artifact that misguides the segmentations. So it's not only just to combine the images, but you also have to repair and make sure that you have nice flat images, otherwise you have the problem of gradients in the classification. So it is not straightforward, but can be solved. Then we can also look into bivariate estimation. This is more a speculative, I don't really know, I have never used it in practice, but in principle from Beer-Lambert's law, we can set up a set of linear equations where we have different attenuation coefficients, and we do some readings here. And then we can, from that, set up this linear equation system or even make it into a least square problem. And with that, we can extract the thicknesses of the two materials. This is an idea what you can do. Probably in a practical application, you would also have to put some distributions on the attenuation coefficients. For one material, you may have pretty good knowledge, but other materials, they have a natural distribution of the attenuation coefficients. Locally different densities, maybe locally a little bit different material, and so on. And to solve that, you may have to go towards doing maybe a Bayesian estimation setup. What you also have to think about when you set up your multimodal experiment is that you may have to do them separately. It's not always that you can do them combined. It can be that the scanners are not even possible to combine, or that they are even in different locations. Could be that in the hospital that you have an MRI and an X-ray CT scanner, and the patient actually has to be transported between the two because they are different machines. In other cases, you could also go towards combined, in particular when you go to material science and geoscience, etc. Then you can set up combined setups where you have both modalities, where you can run simultaneously at once. And then you can also do simultaneous dynamic experiments, which is a pretty neat feature if you can set it up. So, to summarize for the multimodal experiments, and also for the first part of this lecture, what we try to do in a multimodal experiment is to take advantage of more than one modality in order to get clear answer about the constitution of your sample or the process that you want to observe. Naturally, more data is produced. Usually, depends on the modality image sizes, but let's just say you get twice as much data all of a sudden. And the analysis workflow, even though we can use same approaches or same ideas that we have talked about earlier. We still need to adapt them to handle the contrast mechanisms of the two modalities. So we need to have new ideas for how to register. We also need to consider how to fuse the data, at what point we want to fuse it. And also the segmentation has also to be adapted in some way. So this concludes the first part of today's lecture. Thank you for listening.